All right, so quiz questions here. So this quiz is due tonight? Tonight, right? Okay. All right, so let's look at this here for quiz questions. So. For 6 up here, we have to balance this first. And let's see what we got here. Question 6. So if we balance this, you should do hydrogen and oxygen last. So you should do carbon here, and there is 3 carbons here. Put a 3 here. And we have 8 hydrogens here and 2 here. 4 there. And that gets us a total of how many oxygen on the right? 6 and 4 is 10. We'd have a 5 here. So what mass of propane? Question mark grams here. 7.26 grams here. Grams to moles, moles to moles, and then moles back to grams, right? And the mole factor fraction is going to be all right. So there's 6, 12. Well, which one did we look at? We looked at 12 here previously. So we looked at 12 previously. And using the percent carbon of 27.29% carbon. So if we take 0.2729 times 4.772 grams, then we know that 1.289 grams here in the carbon dioxide is straight carbon, and that straight carbon came from here. So we have 1.289 grams of carbon. Then the hydrogen from here goes into the water, and we know that the percent of hydrogen in H2O is 11.19%, or if we take 0.1119 times 1.289, we get 0.1442 grams of hydrogen. And then the rest of this hydrocarbon is oxygen. So if we take 3.15 minus the grams of carbon minus the grams of hydrogen, we get this for oxygen. And then we got to convert these to moles and divide by the smalls to get empirical formula. So you're going to line these all up and convert them all to moles and divide by the smallest. In problem 15, this is just a dilution. Molarity of the concentrated, volume of the concentrated equals molarity of the dilute, volume of the dilute. It's just a dilution problem. So obviously 15 molarity here is a lot more concentrated than 3.6. So we know that this is the molarity of the concentrated or the dilute. Volume of the dilute. And it's like we're looking for the volume of the concentrated. Hmm. 16 we laid out previously. And 17 we laid out previously. Well, 16 and 17 had to be on the board before. So in 16, this is going to give you moles. And then the mole ratio is 1:1. So we know what the moles of nitric acid, HNO3, are. So then we want moles over liters, change that to liters. And 17 we laid out last time. Now 17 was a limiting problem. Because if you're giving molarity and liters, you're going to have moles here. This looks to be 1:1. So what you have here is what you're going to need here. Molarity times liters will get what we have. $18, we must have laid out last time as well. So 18 we laid out last time. Here's all the reaction. Here's everything. All we had to do was convert moles to grams. So you can look that up in this recording when I send it out. Let's see, 23. 23. Okay. So for 23, we have KOH. This, first of all, is that an acid or a base? That's a base. Okay, we know that's a base. Is it a strong base? It's a strong base, right? This is a strong base. This is a strong base. We know that it's going to do this. What's really in that solution, there is no potassium hooked up with hydroxide. We know that this is going to 100% associate into K plus and OH minus. This is going to be labeled 0.00058 molarity. But there is no K hooked up with the OH again. Everything's split up here. Molarity is just a number. This is moles per liter. It's going to be the same number here. And the same number here. Now there's two ways to solve this. We're looking for H3O plus. So we can lay it out both ways here. The quick way is this. We know that the H plus times the OH minus is always 1 times 10 to the minus 14. This is the OH minus. So we know then that the H plus would be 1 times 10 to the minus 14 divided by the OH minus 0.00058. That is the fastest way to do it. Okay, the other way to do it is you could do your POH. Your POH would be the negative log of the OH minus and the negative log of 0.00058. If we take the negative log of that, we are going to get what? 3.24. We get 3.24 here. But that's the POH. That means the pH 14 minus that gets us 10.76. And then the H plus would be 10 to the negative 10.76. Always two ways to do it, right? This accomplishes the same thing, goes more roundabout. This is going to be faster. All right. So that will put the kibosh to this quiz. Let's look at 15 here and where we left off. So 15, chapter 5, not 15. So in chapter 5, we started talking about heat, and we left off, we talked about specific heats. How much heat energy it takes to raise 1 gram of substance, whatever it is, 1 degree Celsius or 1 degree Kelvin. And you could have the molar specific heat as well if you're talking about an entire mole. But typically we do this in joules per gram degree Celsius. And so here are the specific heat values. And then if we can calculate how much heat energy we are going to use, Q is equal to the mass times the specific heat times temperature change. And we left off at this problem down here where we have 85.5 grams of iron. And I'm matching up with this problem. It is at 78.8 degrees. That iron gets dropped into this beaker. The water temperature inside the beaker is 18.8. There is 244 grams of water in here. We're assuming that there's no heat loss. Obviously, this hot iron is going to heat up the water. And in a short amount of time, it's going to dump heat energy into the water. And then the key is that the final temperature of the water and the iron should match. T final is going to be the same for both. So we set that up this way. We say Q lost, heat energy lost, and that is going to be by the iron. The iron is at a higher temperature. That is going to be equal to the heat gained. So we need to know the mass of the iron, the initial temperature of the iron, specific heat of iron. The mass of the water, the initial temperature of the water, and specific heat of water in joules per gram degree Celsius, so they match up. But the key is the final temperature is going to be the same. So when we set that up as Q lost equals Q gained, Q is equal to MC delta T. So for the iron, it's the mass of the iron, specific heat of the iron, change in temperature of the iron. Now, when I left off, the key is to make the temperature changes positive. In this case, we are actually doing T initial minus T final, because we know this temperature is going to go down. The iron is going to cool off. So you want what's in the parentheses here for the temperature change to be a positive number. So we're really going to T initial minus T final. That is going to equal the heat gained by the water. And mass of the water is 244 grams. The specific heat of water is 4.184 joules per gram degree Celsius. And the change in temperature of the water is going to be T final minus T initial this time. So it's not T final minus T initial every time. This is T initial minus T final. Again, we have to make what's in the parentheses a positive value. Okay, let's do this. We can distribute that all the way through, but we need to crank this baby out, right? So let's crank this out. Make sure, grab your calculator. Let's make sure our units are going to cancel out. Grams are going to cancel out here. And we've got degrees Celsius with degrees Celsius. So we're looking good for our units. Our units are going to work out here. If we multiply these two together, we're going to get 39.7365 times 78.8 minus T final. And over here, if we multiply these two together, we are going to, this is probably not the best way to do it. We could divide these out, but this would be fine. 1020 point. I'm just keeping extra numbers because they're still in my calculator. Then T final minus 18.8. So now we're going to distribute this through on both sides. Look familiar, distribute this through on both sides. If we do that, we're going to get 31 point. Just write numbers down that I would have had in my calculator. 39.7365 times T final minus T final is going to be minus 39.7365 T final. And we distribute this through, this is going to be 1020.896. I'm not sure why, I just don't round that to 9. That's so close. Do it minus 8. No, what am I doing? That's T final. And then minus 2.8. So now we want to combine like terms. We want to get T final on one side. Now, I'm going to put this is what I just call cheater's algebra. I'm not going to add. I'm not going to say we're going to add 39.7365. I'm moving this to the other side of the equal sign, making it positive. I'm bringing this to the other side of the equal sign, in this positive. All I'm doing is switching sides. That's what happens in algebra. If you switch sides, all you got to do is change the signs. It just makes it so complicated. It's just so over here, I'm going to have 31 plus 19193. I just made this a 3. I kind of made this a mess. Equals. This is going to be 1020.9 T final plus 39.7 T final. I don't know why. Now, if I add these together, 22,324. 22,324 equals 1060.6 T final. Then if I divide both sides by 1060.6, I'm going to get T final equals 21.0. And make sure when you're all done, it makes logical sense. It should heat up. If we start at 18.8, is it reasonable to end up at 21? That's fine, right? All right, let's look at one. We're going to go to section 5.6 in your book now. So in OWL, I don't think this is switched around. So you might skip ahead in OWL. This section right here was 5.2, I believe. Let me look. This is 5.2. So what we just talked about is 5.2. Then for some reason, it does other things and comes back to this type of problem in 5.6. So we're going to do 5.6, which is called calorimetry. So it's a very similar approach. In fact, it's the same approach. So here's another example. 555 gram chunk of metal is heated to 99.2 and then dropped into a 52 gram aluminum calorimeter cup containing 112 grams of water. The initial temperature of the cup and the water is 10, and the equilibrium temperature is 21.1. Find the specific heat of the metal. So there is a lot here. Let's make 3 columns right in this section and identify what we have. We've got a metal that we dropped in there. We'll just call that X. We've got water. And we have the aluminum calorimeter. I'll just put aluminum cup, if you will. This aluminum cup is going to heat up as well. So not only are we heating up the water, we're heating up the aluminum cup. Let's see if we can identify what we've got here again. 455 gram chunk of metal. $455 grams for the metal. That metal is heated to 99.2. So the initial temperature of the metal I guess I can put an X in there. 99.2. The final. Says all said and done, it ends up at 21.1. We're looking for the specific heat of the metal. It's dropped into 112 grams of water. The initial temperature of the water was 10. The final temperature of everything, it's all the same, was 21.1. And the specific heat of water, well, because we have the specific heat of aluminum in joules. So 4.184 joules per gram degrees Celsius. Mass of the aluminum cup was 52.0 grams. Initial temperature of the aluminum was 10. The final temperature is 21.1. And the specific heat of aluminum, 897. So I typed this one out. So first of all, we've got to identify everything. Then we have Q lost by the metal. So the metal is going to be the mass of our metal, specific heat of our metal, which is what we are solving for. Change in temperature of our metal. We made this positive. In this case, this is T initial minus T final. Now, heat gained. The water is going to gain heat, and the aluminum cup is going to gain heat. So this is the heat gained by the water, plus the heat gained by the aluminum cup. And this right here is actually T final minus T initial. So this is the mass of the water, specific heat of the water, change of temperature of the water, plus the mass of the aluminum cup, specific heat of aluminum, and change in temperature of the aluminum. And it's T final minus T initial, keeping that temperature change positive. Well, we can put some numbers in here now. The mass of our metal is 455 grams. We're trying to solve it for the specific heat. That's what we're looking for. And the temperature change, we can subtract it out. This is 78.1. And the mass of our water is 112 grams. Specific heat of water, 4.184. And our temperature change is 11.1. And the mass of our aluminum cup is 52 grams. Specific heat, 0.897. .1 again. This isn't so bad. We can multiply all that in our calculator as is. So grab your calculator. What do you get on this side? And you should be able to go this times this times this plus this times this times this right in your calculator. It should crank it out. You get 5719 on this right side. Now, let me check my units. Grams, all my units are, I know I've got grams, I know I've got Celsius, and I've got joules. So, in fact, the only thing left right over here is units of joules. So this is my right side. Let's divide it by my 2 over here. So I'm going to divide both sides by 455 grams and 78.1 degrees Celsius. And my units work out. Joules per gram degree Celsius is what I should get. So the specific heat of that metal comes out to be 0.161. Okay, the next one is just like owl problem. In fact, now you're going to see a lot of owl problems come up. I actually have the examples in here. So in the next problem, we got 50 grams of lead. It's at 99 degrees Celsius, is put into 75 grams of water at 4.25 inside a coffee cup calorimeter as shown on the right. I don't have it shown on the right. Capacity of the calorimeter. This is what OWL uses for language. Sometimes referred to as the calorimeter constant, was determined in a separate experiment to be 1.42 joules per degree Celsius. Notice you do not see mass on this. It's not joules per gram degree Celsius. So the mass is figured in. So the mass and whatever it's made up of is already included. It says, what is the final temperature of the mixture? So let's sort everything out again. So right here, first of all, we've got lead. That lead is going to be dropped into water. And then we have the cup itself. So we have our mass of lead, PV, mass PV, 50.0 grams. Specific heat of the lead is 0.159. The initial temperature of the lead is 99.0. So I'm going to go back and double check. We've got 50 grams of lead. Specific heat of lead, it's at 99. It's put into 75 grams of water at 4.25. So my mass of water is 75.0 grams. My specific heat of water is 4.184. And the initial temperature of my water is 4.25. Now, the mass of my cup is built into my calorimetry constant. So my mass, I don't need, of my cup. It has a calorimetry constant, C, equal to 1.42 joules per degree Celsius. The temperature is the same as the water. Determine what is the final temperature of the mixture. We're looking for T final. Okay. We're doing the same thing. Q lost, and this time I typed it out more and more as I went. Q lost equals Q gain. Heat energy lost equals heat energy gain. There's going to be heat energy lost by the metal. What's going to gain heat is the water and the cup. Or Q of the lead equals Q of the water plus Q of the calorimeter or the cup. So that's going to be the mass of lead. Specific heat of lead, change in temperature. And of course, this is the water. This last part's the calorimeter. Now, again, the temperature change here has to be positive, right? As long as you make this positive. All right, let's substitute in here. I'm not going to write down as many numbers this time. So the mass of our lead here is 50 grams. Let me move this over to the left here. So we've got 50 grams. Specific heat of lead is 0.159. (99 degrees Celsius). It's T final. My mass of my water, 75 grams. Specific heat of water, 4.184. A change in temperature of my water is going to be T final minus 4.25. Plus, I don't worry about the mass of my calorimeter. It's 1.42 joules per degree Celsius times T final minus 4.25. So T final shows up in 3 places here. So now it's just cranking it through, right? Cranking it through. So if we take these two here, this is the 3 sig figs, 7.95. This part right here is 313.8. So now let's distribute those through. So 7.95 if you multiply these two. A second. And still T final minus 4.25, right? So if we distribute this through, we are going to get 787 minus 7.95 T final equals 314 T final minus 1334 plus 1.42 T final T final minus 6.035. So at this point, let's get all the T finals on the right. I've got 313 T final on the right. I've got a positive T final here. When this comes to the other side, instead of minus, it's going to be positive. So I just say, throw your T finals on the right, throw your other numbers on the left. And you're just changing the signs if you're crossing the equal sign. That is the effect of algebra. The math teachers make it sound more complicated. So here's my constant numbers. I got 787. This negative 1334 is going to be positive. This negative is going to become positive on the other side. So on the left, I'm going to have 787. I'm going to add 1334. I'm going to add the 6.035, although that's way out of bounds for sig figs. I could just leave that at 6. I'll just put it like this. Equals. I'm going to have 314 T final. I'm going to bring this one to the other side, and it is going to be plus 7.95 T final plus 1.42 T final. On this side, we get 2126. And on this side, we get 323 But solve this. We're just going to divide by 323, right? Divide both sides by 323. .58. Just quite a bit. If you can summarize it like this, if you can get this down, summarize it, and then Q lost equals Q gain, eventually you're going to solve this, right? Not super complicated. Now, the next page has an exact OWL question, and then I solved this, and I got my butt kicked because of this. Because I did not use the OWL value for the specific heat of lead. Now, OWL uses lead specific heat of 0.159. I don't know if I went to Google or I had some table. I don't know if I went to the back of a textbook. I used, wherever I found it, 0.1256. That created a nightmare because my answer came out negative. So when you do these problems, there is not a nice locked in chart for specific heats. They seem to vary somewhat. So if you're doing the questions in OWL, use OWL, I think has a chart in there. Use those values. Otherwise, you'll be doing what I did. I was like, what the heck? And then by the time you do a long problem like this and you get a negative number, I went back and searched and searched and searched, and then there was only one solution finally at the end, and I researched that number. So this is directly from OWL, and I cut and pasted it. So in the laboratory, a coffee cup calorimeter or constant pressure calorimeter is frequently used to determine the specific heat of a solid or measure the energy of a solution phase reaction. Since the cup itself can absorb energy, a separate experiment is needed to determine the heat capacity of the calorimeter. This is known as calibrating the calorimeter, and the value determined is called the calorimeter constant. One way to do this is to use a common metal of known heat capacity. In the laboratory, a student heats 91.25 grams of lead . And the initial temperature of that lead is 99.32, and drops it into a cup containing 81.85 grams of water at 215. Final temperature is 2719. What we want to do for this problem is calculate the calorimeter constant. And notice it's in joules per degree Celsius. Mass is not in here again, right? Mass is not in here. So we know that this lead at 99.32 dropped into water and the cup. So the water and cup are at the same initial temperature. The lead is going to cool down. The water in the cup are going to heat up. In fact, they heat up to 24.15, goes up to 27.19. So let's do the same chart to make sure we've got everything here. So we're going to have some lead. We've got some water, and we've got the cup again. as much until we have to extend it. Now, our mass of lead, 91.25 grams. And our specific heat of lead is 0.159. Our initial temperature is 99.32. Our final temperature is, everything's going to be the same, 27.19. Let's just do our change in temperature. We'll put that into the equation. So my temperature changed by 72.13. My mass of water, 1.85 grams. Specific heat of water, 4.184. So temperature 24.15. And my final 27.19. Stop my line right here. The change in temperature of the water in the cup are the same. So let's go up here. My mass. We don't need this mass. You're looking for calorimetry constant of the cup. We'll call it C cup. Temperature of the cup. Same as the water, 24.15. And the final 27.19. This temperature change is the same for both. So the same exact solution technique. We know that Q lost by the lead is going to equal to Q gain. And that's going to be the water plus the cup, right? Now let's see if we can work this smarter. Write this out. So this is going to be, the mass of lead, specific heat of the lead, change in temperature of the lead, right? Equals mass of the water, specific heat of the water, change in temperature of the water, plus calorimeter cup constant times the change in temperature of the cup. two are the same. We know what these are. So let's see. Would it help to factor that out? We could factor that out. I'm trying to figure out a way to solve this without turning this into a mess quickly to solve it. This is the same number, right? This change in temperature here of the water in the cup is exactly the same. So I could factor that out of there. No, we're going to solve it this way. We can subtract this from both sides, right? Let's just do that. Subtract this from both sides and don't plug in your numbers yet. So if we subtract this from both sides, then we can get that and just divide by the change in temperature of the cup. We've got it. So let's stick our numbers in last. It's a lot easier to solve it and then stick your numbers in. So then we know that the mass of the lead, specific heat of the lead, change in temperature of the lead, minus the mass of water, specific heat of the water, change in temperature of the water. I should just put change in temperature for that. It's the same thing, but I'll leave it like this. That equals specific heat of the cup times the change in temperature of the cup. So I'm just going to take this. I'm going to divide both sides by the change in temperature of the cup. It's going to be a lot easier. That's going to leave my value I'm looking for. Change in temperature of the cup. That's all right. So now I've got it all solved. I don't have to factor anything out. I don't have to distribute anything through. So let's put our numbers in here. We're going to have 91.25 grams. Times my specific heat of lead, 0.159. My change in temperature is 72.13 for that. So that's my mass of lead, specific heat of lead, change in temperature of the lead. My mass of water is 81.85 grams. Or 0.184. My change in temperature of my water right here is 3.04. All of that by the change in temperature in my cup, which is 3.04. Grab your calculator, see if you get what I got here. Grab your calculator. You can see when I use the wrong specific heat and I started backtracking, it ends up being a nightmare. Calculator, see what you get. Do the numerator first, right? I got 1.79. Anybody else? 1.79? All right, 1.79. So 1.79, that's going to be in joules per degree Celsius. Okay. So poke around in OWL. This should be OWL part 1 yet. Chapter 5, part 1. It is. Oh, I think. Yeah, I'm hoping this is pushed into part 1. You may actually have to look for this in OWL part 2. I got to double check. But you can always open up OWL chapter 5, part 2, right? And look to see is the problem calorimeter constant, something like this. It's now what OWL does. Well, this is why we skipped up to here, because 5.3 talks about changes of state. So it didn't seem to make sense to go into 5.3 and then 5.6 comes back to calorimetry stuff. So here's 5.3. So energy and changes of state. So changes of state, what we mean for changes of state is solid, liquid, and gas. So let's look at what we've got here. So this diagram here is how much energy it takes for 1 kilogram of ice in kilocalories. 1 kilogram of ice at -40. We need to heat it up. We need to melt that 1 kilogram of ice. This is how much energy it takes. So notice it does not take much energy to heat that ice up. But before we can melt it, what we're trying to do is we're trying to take that -40 frozen ice to steam. And we don't have the temperature, maybe 160. I don't know what it is to steam up here. Now, if we are going to add up the total energy, we're going to have this part right here. In order to calculate this energy, it's going to be Q is equal to M times the specific heat of ice and change in temperature of the ice. That's just that calculation. Then we have to melt the ice. There's a table for melting the ice or melting anything that's a solid. So here is our table. That is called the latent heat of fusion. Now this is to go from a solid to a liquid or vice versa. Now remember, we're talking phase changes. Solid to a liquid. Focus. Symbol for this is triangle H, means delta H, and for fusion, FUS. This is the heat energy to either melt something or freeze it from a liquid to a solid. Notice the units are in joules per kilogram. But if we are in joules per kilogram, you know that 1 kilogram is 1,000 grams. So if you want it in joules per gram, we just divide by 1,000 or move the decimal 3 to the left. And we need to know the boiling points. We need to know the melting points. Then if we are going to take a liquid to a gas, latent heat of vaporization, this is a liquid to a gas. Or do we need to cool it down to go gas to a liquid? This is the enthalpy of vaporization. So now let's go up to my diagram. First thing you have to do is get the ice up to the melting temperature of ice, which is 0, right? That is a separate specific heat for ice. Then right here, this flat line, you still have to put energy in, right? You have to melt all of your ice. This right here, Q is equal to the mass times the enthalpy of fusion. Okay, there is no temperature change. It melts at 0. Then once you have, this is solid ice at 0. Over here, you have all liquid water at 0. Then you have to heat up the water. So here, of course, this line is Q is equal to MC of liquid water. I'm just going to put H2O, and the temperature change there is always 100 degrees Celsius, right? Right here, we have liquid water at 100. And by the way, you can see the values here. I'm changing my temperature by 100 degrees, and it takes, this is in kilocalories. That takes 100 kilocalories. But the big one that takes all kinds of energy is this. The phase change to change all of that liquid water at 100 to H2O gas at 100, right? This value right here is Q is equal to M times the enthalpy of vaporization. Then we have to raise the temperature, which is going to be Q is equal to the mass, the specific heat of H2O gas or steam. I'll put the word steam in there, and the temperature change. So next time we meet, let me see what we're going to be able to do for the quiz. We'll talk about this. If we were calculating this, we would have to do 1, 2, 3, 4, 5 calculations and add them all up. 5 calculations and add them all up. on this quiz from chapter 5, I'm just going to add through 8. 1 through 8 on chapter 5. I only added one question. Wait a minute, that doesn't sound right, I guess. And 10. Try 10 as well. 1 through 8 and 10. All right, have a good day.